Hi, we are the wonderful Wingnuts. I'm Jackson.
I'm Kai.
I'm Spencer.
I'm Krupik.
And this is our A301 engineering project.
We began by looking at the stakeholders for our aircraft mission. The first stakeholder is the aircraft team, which includes the pilots, the maintenance crew, and other servicing members of the aircraft. Next, we have the design team, which is ourselves, who are the chief designers of the aircraft and are required to complete all design requirements for this project. Next, we have the governing bodies, which include the FAA, the FIA, and the National Air Championship race officials themselves. Next, we have the team sponsors, who are the companies that are providing the income for our aircraft to be built as well as designed, and they're necessary for us to get off the runway. Next, we have our competitors, who are the aircraft that we'll be flying against, and the pilots, who are concerned over safety as well as a fair competition. And then finally, we have our aircraft fans. For the design requirements, we went over a few basic steps here to decide what the needs of our stakeholders were and then the requirements needed to fill each of those needs. To start, we have certification and inspection, which includes passing with the FAA, the FIA, and the National Championship air race officials themselves. And that's in order to have a safe aircraft that can compete in the competition safely, as well as legally. Then we have our traditional flight capabilities, which is the ability to take off and land at a traditional runway. In this case, we used an airfield with a 10,000-foot runway, clean conditions, and an elevation of 3,500 feet to be representative of the airport that we will be taking part of for our aircraft flying in race days. Then we have our successful race completion. In this case, we are looking to complete the air circuit in a competitive time to give us the best advantage to win. Then we have our aircraft performance, which includes engine performance as well as aerodynamic characteristics and safety margins in order for our aircraft to not only be successful and compete, but also to be safe. We then have project design requirements, which include things like the number of engines, the payload, and the airframe itself, and how those need to be designed to fulfill project requirements in themselves. And then finally, we have the flight conditions that our aircraft needs to be capable of flying in, such as different weather and wind conditions that the aircraft can face. Next, we began by looking at a preliminary risk assessment for our aircraft. If we look up here, you can see that there is a table that includes both post and pre-mitigation for the risks. And post-mitigation, most of the risks are in the green, but we can still see that there are some in the yellow. This points out the fact that the aircraft mission in itself is very dangerous, as all air racing will be. Next, to begin our design, we began by looking at the reference aircraft. Four most prominent racers that also have a lot of available data include the North American P-51D Mustang, the Grumman F-8F Bearcat, the Vought F-4U Corsair, and the Hawker Sea Fury, all of which have histories of success in the unlimited class of the National Championship air races. The actual beginning of the aircraft design starts with an assessment of the initial gross takeoff weight of our aircraft, and we did this by using the sizing algorithm that we've used throughout A301 class. In this case, we ran this code through MATLAB and ended up with a final result that is around 8,800 pounds for our initial gross takeoff for our aircraft. After looking at the aircraft's initial gross takeoff weight, we then looked at atmospheric considerations. In this case, we're looking at the typical conditions around the Roswell Air Center, which is the airport that the race will be taking place at. Here we can see, looking at the slide, that the average temperature is around 90 degrees, which is slightly above average for standard temperature, but the density is well within a considerably normal range, as well as having relatively calm winds, all of which are very advantageous for flying.
Next consideration of the design parameters was wing loading. Our first step in calculating wing loading was to first check if maneuvering limits would interfere with it. By doing this, we used the equation in the upper right, which would relate speed to G's. And as you can see in that upper right table, we have various speeds that the aircraft might be operating at, and then their G's. You can see that at our target of 500 miles per hour, the G's are relatively reasonable for an aircraft of this type. So we concluded that we are not limited by maneuvers, but instead by stall speed. To get our wing loading thus, we plugged in our stall speed target, which was 100 miles an hour, to this equation, which resulted in a wing loading of about 38 pounds per square foot. To carry on from that, we have the wing geometry. Start off in the upper right, we have the wing area, which is a direct next step from wing loading and getting the weight of the aircraft. And that turned out to be about 230 square feet. Now we have the aspect ratio, which came out to be about 5.9. This was taken pretty directly from some of our reference aircraft, in particular the P-51. With SREF, we were easily able to get things like the wingspan, chord, and other information. Finally, we have the airfoil of the wing. So to do this, we had to get Oswald's efficiency, and that came from this equation of empirical correlation for Maymer in the upper right, where we essentially plugged in our aspect ratio and got a pretty clean 0.87. We plugged this into various plots. We looked at various plots from Nikolai, including these two, and eventually came to the NACA 6409, which is plotted in the lower left. For tail sizing, we also used references from Nikolai. In particular, we have the table on the upper right, which has various general sizes, coefficients for the horizontal and vertical tail. In particular, we were interested in the military jet fighter because we thought that struck a clean balance between something like a single-engine general aviation plane and something more aggressive like a jet fighter. With those coefficients, we plugged it into these two equations on the left, which gave us a range over various tail arms. We eventually selected the middle of these tail arms, which were from the reference aircraft again. So then we have a horizontal tail area of about 50 square feet and a vertical of about 30 square feet. To finish off the controllability and tail sizing, we also wanted to make sure that our pilot always had control of the aircraft. To do this, we applied with the 15 to 35 pounds of requirement on the stick, using these relations given by Etienne on the right. These relate pilot input to essentially gearing, and by looking at these relations, we could tell that we could achieve any type of power we wanted for the pilot based on a certain gear ratio. In addition to purely relying on gear ratios, we also compared our calculated tail areas to various reference aircraft, and came out that given that our World War II warbirds could do these relatively high load maneuvers, so could we with a pretty similar tail area. Our tail airfoil is the NACA 0012, which is again plotted in the lower right. Another important consideration for this aircraft is our takeoff and landing distances, because obviously we do not want to be overrunning the 10,000-foot long runway at Roswell. To do this, we created a MATLAB script which incorporated the two equations in the upper right, the top one being for landing, the bottom one being for taking off. Plugging into these equations are various inputs we've already discussed, as well as a sigma that was calculated by using the actual air density divided by the sea level air density. And in the bottom left, we have calculations for our thrust-to-weight ratio. This script eventually gave us an output of a takeoff distance of a little over 1,000 feet and a landing distance around 3,000 feet. So these are clearly well within the range of Roswell.
Alright, so the next part of our aircraft sizing is finding our L/D ratio. To do that, we start with the drag coefficient. We basically just find the drag coefficient for any different contours on our aircraft. That includes the wing and tail, fuselage, and canopy. And as you can see, we use the equations above listed on the slides, and we just add them together. Okay, using that, we can find our drag polar curve, which we can then use to find our optimal L/D ratio. And then from there, we can conduct some performance analysis on our aircraft. So first, we graph the drag coefficient versus our flight speed. And then from there, doing a bit more math, we can get our drag in pound force. Next, we can do a bit of performance analysis. First, we graphed our drag coefficient versus our flight speed. And then doing a bit more math from there, we can get our drag versus the flight speed. And the main thing here is that we want our cruise speed, which we know has to be less than 500 miles per hour, and we're looking more or less above 200. And we want the least amount of drag there, which you can see on the graph above. And then from there, now that we know our optimal L/D ratio, we can use that in our range calculations and endurance calculations using the Brouguet equations. Then we can also from there get our rate of climb, which we all do in MATLAB for our aircraft sizing.
With those, we can find the max speed. So we decided first on the engine, which is the Napier Sabre 7, which gives us 3,000 horsepower, which is a lot for our plane. And to find the max speed, you find where the power available is equal to the power required. And with this, we get around 500 miles per hour, a little less, but that's very competitive in this class of racing. So now you might be wondering how we got to all these calculations. So we'll go back a little bit to the first parts where we created the aircraft generation. So we created three concepts, which were First, it was a P-51 that was heavily modified to fit our criteria. The second design was much more theoretical. It was basically a completely new plane, very lightweight, little less power, but it was still overall very good at design. And then option 3 was kind of a mix of 1 and 2, so it was more standard, used a lot more of the P-51 body, but we used some of the new designs, such as a split tail wing. And so some of the key features we were looking for on this were unswept wing because we're below supersonic, retractable gears to reduce drag, and a single engine to maximize power while minimizing weight. Next, we have our aircraft selection. So we made a table to compare each of our criteria, which we based off of the requirements, to best estimates of what we thought each aircraft could achieve. So after this, we created a little bit of scoring based on the criteria, and then we weighted them. So the weights were based on what we found of our biases of what's most important. And so our criteria were weight, power, velocity, complexity, and range. So we rated complexity a little higher because it's our first year. We want to prioritize safety because, of course, if you can't finish a race, you're not going to win. And we minimized range because range, although it's important, we don't need it as much in the race because the race isn't too long. And so in the end, design 1 and 3 were very close. So design 3 actually won in the raw scores. It had a better score overall for all the categories combined. But design 1 ended up having a better complexity score, and therefore put it ahead, and that became our main selection. So our final design, the Wingnut Wonder, as you can tell, very rough sketches, but it's a nice design that we will work on constructing to win this competition. Next, we have our lessons learned. So through this process, we learned a lot. First, engineering takes adaptability. We had countless designs, we thought we were going well at some points, we realized we were going completely the wrong direction. But that taught us that adapting and working through this is what's most important. And next, we learned to work as a team. It was a long project, a lot of data, a lot of numbers. It's important to work as a team. You really get that camaraderie, but also it makes the work go by a lot faster. Next, not every idea works out. We had countless ideas, theoretical, things that we've seen on like Instagram, it seemed really cool. But in the end, we decided to go with a little safety design because not all ideas work out. And although we want to explore those ideas, once again, we decided that, complexity adds challenges, so simplicity is best. And lastly, success comes with time. This is our first year. We might not succeed in the competition. We have confidence that with time, we will keep iterating our design, and we will win. Thank you for watching. We are the Wingnuts.